We started chapter 14 with black body radiation. We met a fellow called Max Planck, right? A physicist trying to solve some problems. We're going to see him again in chapter 15. Anyway, hot solids emit energy as electromagnetic radiation. The higher the temperature, the shorter the wavelength, and the higher the frequency. That's what we see. Wave theory, though, cannot explain this. Wave theory says you should just keep having more and more and more output and shorter wavelength until it disappears, until it goes ultraviolet. Well, things don't disappear when they get really hot. They just get whiter and brighter, right? So why is that? And the reason is because the hot molecules are emitting energy in bundles or lumps at specific wavelengths tied to the frequency. That's what's happening, right? And only particle theory can explain that. So that led us into the photoelectric effect. First observed by Heinrich Hertz, light causes electricity, explained by Albert Einstein with his phototube thought experiment. You can actually build this, it does actually work. Right? But they're expensive, that's why we use LEDs, because they're pennies, as opposed to these which are, hundreds of dollars. Okay, so it's an easy experiment when you've got so many to do. You should understand and appreciate how this works. This is, I've seen that on exam papers, of course. I don't remember if I've asked anything about it tomorrow, but it doesn't matter. So you've got your two metal electrodes, and you shine ultraviolet light on one of them, that becomes our cathode. The anode is the one that accepts the photoelectrons once emitted, measured by the ammeter, and the battery is there to generate a field, assisting or repelling those charges. So from this experiment, Einstein saw that a minimum frequency of light is required to make the thing work. That's the concept of the threshold. The current that is generated is exactly related to the intensity. It's a one-to-one relationship. More photons in, more photoelectrons out. You do not change the energy of them, though, by making the light brighter. You only change the number. If we reverse this battery, we reverse the field, and now we can get to the kinetic energy of the electrons, because that voltage that stops them, called the stopping voltage, times the charge, gives you their kinetic energy as they're ejected from the surface. We then took all of this information and produced a graph of energy versus frequency, so energy of the electrons versus the frequency of the photons, the slope of which always provides Planck's constant in one of its two forms, right? If you've got joules here, you get joule seconds. If you've got volts here, you get EV seconds, okay? So depending on what axis you've got will determine the unit of the slope. The intercept is important. That's where the beginning of the photoelectric effect occurs. And the y-intercept, of course, gives you the work function, should you need that. So we have excellent notes, conversation, and now assignment on all of this that you did. And a lab, too, right? So then we talked about Compton. So Arthur Compton studied the effect of X-rays